Hello everybody, this is Tortoise or Check, and today we'll have a look at logical connectives, statements with value of true or false, or logical gates. It doesn't matter like which way you'll take this problem. So first we need some inputs to do. This will be the basics of high school, so hopefully it will be understandable, but don't expect like anything too complicated here. It'll be just a revision of something that you'll probably learn at school or you did. Okay, so I will combine these three views into each other, like as we go. So we need some inputs, as I said, because we want the operators. Every time we'll have an operation, it will always be an operand, let's say operand A, then some operator, because usually all the operations we'll do will be binary, so we'll need another operand, and that will be called B. Sometimes for unary operations like negation, I'll just use operator A. Okay, so that's what we need, and like this is the view of bitwise operations. If we just look at A and B as some binary numbers with, not binary numbers, but just bits, therefore 1 or 0, then we can do bitwise operations. But we can also look at them as logical gates. In that sense, this will be the logical gate, the operator, which will be either AND or XOR or the stuff you've probably seen. And the operands will have just a value of 0 or 1, as for the bits. So it's like the same thing. And the last view will be that we have a statement, some statement A and statement B, such statement that we can somehow tell if its value is true or false, or in other words, not that we can tell, but it makes sense to like value the truth value of the statement. Okay, so now we'll have always, as I said, 0 or 1, where 0 corresponds to false, which I'll denote as probably just F, or 0, I'll prefer those, and for 1 it will be true, meaning that the statement is true, the operand has a value of 1. So let's get some logic gates and just revise what they actually do. So I have here 4 columns of different variations, permutations of these bits. We have 1, 1 situation in the first column, 1, 0, 0, 1, and 0, 0 in other columns. This means that in this column, both of the statements A and B is true, or are true. In this, only A is true and the B is false, vice versa in the third column, and fourth column is false for both. Again, in the logical gate view, we can just assume that those are bits, and here the first input is 1, the second input is 1, here first is 1, second is 0, and so on and so on. Therefore, the order may be important for some, like implication, but usually not, because I think the implication will be the only one that will actually need the order from those that we'll have a look at. Okay, and now, first operation, you probably know, is called a conjunction, denoted with this little roof. So that's conjunction. I'll probably make this a bit smaller. Okay, and it can also be denoted as AND. So maybe I'll add a column for the actual name. Okay, so this is an AND. This, in the world of statements, means just that both statements have to be true at the same time. For example, okay, I have to pass my mathematics exam and as well my IT exam. If I don't pass any of these, then, well, I didn't pass. So if I say I passed mathematics and IT, and I didn't pass one of these, then I lied. Therefore, these values are all false, and the only time I actually told the truth is if I actually passed both of these, if and only if actually. So the AND value or the conjunction is true only where both of the statements are true. Okay, so that's the first one, the easiest one, probably one of the easiest. The second one is a bit similar, and it's called a disjunction, and it's denoted with this little vector. So that would be disjunction. And in logic gates, it is usually denoted as OR. So if you have an OR logic gate, then that is this operation. And what OR means in statement world, that you actually need at least one of the statements to be true. For example, if you say, okay, I'll go to the cinema, or I'll go, I don't know, I'll visit my grandma, probably I'll have enough time to do both, but if I don't do any of these, then I lied. But if I do at least one of those, then I told the truth. So the disjunction or the OR operator needs at least one input, either one to be truth. So if I visited my grandma and went to the cinema, then it was still good. If I did at least one of them, it is still good. So this is at least one true. The only way where it's false is if none of the statements are true. Okay, so that's disjunction. Let's continue. I'll just quickly add some rows here. So the third operator is very similar to the disjunction, and it is denoted as sorry, I always forget where this goes. Yeah, I thought so. It's denoted as a little vector but with a bar below, and it's the same thing, just exclusive disjunction. The exclusive part, disjunction. The exclusive part means that it cannot happen at the same time, and the logical gate equivalence is XOR, where the X means the exclusive part. So this cannot happen at the same time. For example, in the world of statements again, like if it's simply impossible to do that at the same time. Like if you say, okay, I'll either go to the concert, or I'll, I don't know, play with my friends. If that's the situation that's happening at the same time, and I cannot be at the two places at the same time, or like do it at the same time, then if I played with my friends and as well with went to the concert, then this just wouldn't make sense, and therefore I'm probably lying. So that's kind of not the mathematical explanation, but that's what it actually does. So the operator XOR needs not at least one input to be true, but exactly one of the inputs to be true. So that's the difference. We have our inputs here. Notice that in the second and third column we have exactly one out of A and B to be true, and in the first and fourth there's either both of them or none of them. and in both of these cases, exclusive disjunction is false. So that's XOR. The difference between OR and XOR is in the first column, as I already explained. Okay, and now we have implications. I'll have here probably left and right implication. So for A implies B, the implication is denoted by the little arrow. It's implication. This is the left implication, meaning it's from left to right. But that's usually how it is. And it doesn't have an equivalent, actually, in Logické. How to do it? Just like this. Yeah. So, just the little arrow. Now the order matters. And this is actually the most confusing one, I would say. What this does is, I don't know, I will probably start with the example from the statements word, and then we'll derive the actual values of it. So, let's say that we have A to be it's raining, and B to be streets are wet. Then the implication, what it does is it adds if, and then if for the part on at the beginning of the arrow, and then before the part of the end of the arrow. So this would be if A, then B. That's how you would read it. And if I use the example I gave you, this would be if it rains today, let's say, the streets will be wet today. So if it rains, the street will be wet. Well, that looks like it will be true. So if the both statements are true, it's raining, and also the streets are wet, yes, then it sounds like I told you the truth. If it's raining and the streets are not wet, well, I said if it's raining, then if it rains, then the streets will be wet, then I lied. So this value is false. Now let's jump over the third column, which is the most tricky one, to the last column. It's not raining and the streets are not wet. Well, I said if it rains, the streets will be wet. If it doesn't rain, so I didn't say anything about when it doesn't rain. So this is still true. I didn't specify what will happen when it will not rain, and it makes sense that streets are not wet. So this statement is still true. And what about the last column we left off, the third column? Well, it is not raining, but the streets are wet. I said if it rains, the street will be wet. Well, it's still not raining, but the streets are wet. Could this happen even though I told the truth? Well, yeah, in some cases. Like if you imagine that someone's just, I don't know, washing their car at the outdoors, then the streets can still be wet even though it's not raining. So in this case, this is still true because again, I didn't specify what will happen if it doesn't rain. So this is still true. So in other words, implication, I have two things to say about it. Implication, it's only false when the part at the beginning of the arrow is true and the part at the end of the arrow is false. So like the first input is true and the second input is false, then and only then the implication is false. Also, the second thing, if the first input is false, then the implication's value is always true, because again, we didn't specify what will happen in that case. And similarly, like the implication from right to left, it's the same thing, just, you know, from the other side. So I can just copy everything. This is implication from the right. So the first input here is bravo, B. And again, we know that these cases are true. And we said the only case when it's false is when the statement at the beginning of the arrow, so the first input is true, it's true, and the second input is false. Now, the first input is bravo, because this is at the beginning of the arrow. So, when it's true, okay, these two cases, and also A, the second input, is false. Okay, that's only this. So we have the first third column false in this time, and everything else is true, because it's implication. So that was the hardest one, I would say, probably. And now we have 4 more things I want to specify. So first, let's move this actually, so that will be better for us. 1, 2, 3, 4. Okay. Okay. So first is this one, either with single arrow. This all can be double arrowed actually. I'll probably just change that because like single arrow is often used in, for example, KTaNE. However, in mathematics, we'll usually use the double arrows. So I'll use double arrows. And this is called equivalency or biconditional. I'll put there biconditional. Why biconditional? Well, you can see that this is kind of implication from left to right, and at the same time implication from right to left. Therefore, this by the way does have an equivalence in logic gates, and it is called XNOR. You've probably seen that. So note the similarity between XNOR and XOR. We'll go over that as well. For XNOR or biconditional in the statements world, it actually means if and only if. So this was AND or exclusive OR, meaning that they cannot be at the same time true. Implication is if then or if then from right to left, and now we have if and only if then. That means that A is true if and only if B is true. Therefore, they have to be true at the same time. So let's just look at our same inputs. Here we have A is true and B is true. Yeah, they are true at the same time, so this is true. Here we have different true values. A is true, however, B is false. So this cannot be. In other words, this is false. This equivalence is false. The same about this column, because like the order in the equivalency or biconditional doesn't matter, since we have implications both ways. So this is just symmetric, and we have zeros here and here. And now for both zeros, well, I said that it has to be true if and only if both of them are true at the same time, but they don't need to be true necessarily, because here we don't have A being true, but and at the same time B is not true as well. So if we get the pieces together, then none of those are true. Therefore, yes, they are true at the same time, because none of those are true. So there are no these cases where there would be exactly one of them. In other words, we need either both to be true or none to be true. And there's certain thing going between XOR and XNOR, which we'll cover in a moment, actually right now. And it's about negation. Negation is the only operation that is unary from those that we'll go over. And what that means, let me just put here the thing, yep, negation. What that means is that it just takes the statement, whichever, it can be negation of even like complex statement, not just A or B, and it negates all the values. So if it's 1, it returns 0, if it's 0, it returns 1. So we just have a look at the row of A, and we negate that, then we'll have the opposite values, meaning from 1 it will be 0, 0, and now from zeros it will be 1, 1. So it will be 0, 0, 1, 1. 0, 0, 1, 1. And Logické equivalence is not. So if we say not alpha, it means the opposite value of alpha, where alpha is the statement or the logic gate or the bit. It doesn't matter. Like not logic gate, but logic gate input, actually. Yeah. So that's what negation is. And if you'll just have a look at XOR and XNOR, then note that these bits and these bits have something in common. Actually, to be more specific, they have nothing in common. In every column, there's negation of this bit in this row. So the XNOR biconditional is actually a negation of XOR, the exclusive disjunction. So they have the exactly opposite values, and therefore in schools the XOR is usually omitted and just biconditional is taught. So yeah, that's what we have. The N here means denote, the negation, and it's just like, okay, XN is important because it's not exclusive NOR. We'll go over that in a second, but this is just a negation of XOR. But now, okay, we negated XOR, actually. What would happen if we negated AND? Well, if we negate AND, then it could be denoted as this, negation of A and B, negation of this. But also, it can be denoted just as A vertical bar B, meaning NAND, where NAND is just negation of AND. So this will be negation of conjunction. In other words, it has also like the name in English, it's called alternative denial. But that's just a formality. Let's have a look what it does. Well, it's a negation of AND, so we'll have a look at the outputs of AND, these, and we'll just negate them. So it'll be 0 and 3 ones. In other words, NAND is true anytime it doesn't have both inputs to be true. So NAND is only false if and only if false when both inputs are true, and true otherwise, of course. Okay, so that's our NAND, just negation of AND. The same with NOR. We can just negate OR. That has also a name, and it's called joint denial. Mistake. And again, we could just note it as negation of OR, but also we can use the arrow, down pointing arrow, which means NOR, being the negation of the disjunction. So we just negate all of the bits and get 0, 0, 0, 1, and that will be the negation of OR. So 0, 0, 0, 1. As you can see, NOR is only true, if and only if true, when we have both inputs to be false. So it's somehow like the equivalence of AND of the conjunction. It has also only one of these 4 possibilities to be true. However, it's the opposite way. Here it has to be both truths. Here it has to be both false inputs. And this, like, we can use the same view for NAND and OR. Here we have only one like situation where it's false. For OR it was when both inputs were false, so like as it makes sense. And here we have NAND, which is the negation variant of AND. Therefore it's like the other way, meaning that if we have both inputs true, then it will be false, and only if. So yeah, that's how to remember those two. And are we still missing anything? Yeah, we got, I think, almost everything. Of course, we could negate every single one of these. You may also ask, like, what would happen if we just, I don't know, negate implications? Well, if we negate left implication, we just get some operation or operator that would be yield 0, 1, 0, 0 for these cases, respectively. And so it'll be true only and only if the first input is true and the second input is false. And now you can see that we're actually kind of, as I said it, I'll repeat it once more, we're mixing the logical connectives. Once more, it is the negation of the left implication, and now, note, is true if and only if the first input is true and the second input is false. So we're just mixing it. So I can just put it here. Negation of the implication is true if and only if we have the first input to be true and the second input is false. So we have the negation of it. And so on and so on. We could the same way negate the right implication from right to left, and we would just get that it's true only if Bravo is true and alpha is false, and so on and so on. Of course, I have just, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, but the not is unary, so just 8 binary operations. Binary means that there are 2 operands. Unary means that's just 1 operand. And so that's 8 operations, but note that there are 4 bits in the, this is input, but in the output. And those bits can be either 1 or 0. So if we just put like calculate all the possibilities, then we have 2 possibilities for the first bit, 1 or 0, 2 for the second, 2 for the first, and 2 for the first. That's 2 to the power of 4, which is 16. So we have actually 16 possibilities. So 16 actual binary operations that could be used. One of them is this one, because we don't have like this one anywhere. But this is a binary operation that could be like denoted somehow, but it's not, because it's creatable just using these. It's provable that we can just use, I don't know, I think conjunction and negation, and we'll be able to like create every single one of these operations. But it's usually like easier for us and more comfortable to use all of these that you see here. Okay, so what would be the next like missing ones, the 18 missing ones? Well, actually 6 missing ones, since we have already these 2. Well, just negations of those that we don't have here. We have XNOR and XOR, we have AND and NAND, we have OR and NOR, but we don't have like, I don't know, these, and so on. Like the weird combinations where the order matters, or order of the inputs, because of the difference of the output from the second and third column. So, like, okay, that's something, but we usually don't need that. And if we do, it's just like more natural for us to create it from the already existing logical connectives or binary operators or logical gates. Like it's the same thing essentially. And also, of course, we have operations or operators, that are just zeros. We have just 0 or just 1. I may just split this because it's like the same thing. Then it's just a constant. This is constant 0. And the second one is constant 1. And what this means, well, of course, it's noted as a 0, and this is noted as 1. And what that means is, like, it does need inputs. However, it doesn't matter what the inputs actually are. It just always yields 0 for the constant 0, 1. And this just always yields 1. So, like, they're kind of useless. Like, if you think about it, it will take 2 inputs and yield just 1 output. So it will consume essentially an information, and actually it will not use any of these inputs. So it will just completely destroy all the information. So that's a showcase of how useless some operators can look. Maybe they are useful in some way, but like for normal humans, or at least for what we are teaching or learning at school, it doesn't actually matter. Okay, so I think we'll leave it at that. One last thing I will show is just Venn diagram view of these, and I'll probably just use something that's already existing, so I don't need to create them. Okay, I'm taking this from the Boolean Venn diagram from Controlling, and nobody explodes. So this is how they look. If we have AND, I'll just record them for one. Yeah. If we have AND, then as we said, it's true if and only if both inputs are true. And in the Venn diagram, it means it's true when it is inside the circle. So this is X-ray circle, meaning that it has true value in both these purple sections, and the Yankee one, or the Y one, is true in these purple sections. So the intersection, essentially, which is again, or not again, actually the first time in this, it's a set operator. So intersection, it's the fourth view for this problematics, and you can see that intersection is actually denoted similarly to AND, and that's actually like another mnemotechnical thing you can use. So it's true if and only if both of these are true. For all we have if at least one of them is true. So it's this is only X, this is only Yankee, this is both of them. In all these cases, it is still true. XOR has the difference that now we don't take the intersection because we cannot do both things at the same time. So this is only X-ray, only Yankee, meaning we need exactly one of those to be true. Implication, as we said, it's true, and it is false if and only, I kind of screwed that up. It's false if and only if the first input, being X-ray, is true. So it has to be one of these fields. And at the same time, the second one is false. This is still in a Y circle, so this is incorrect. So this is the only one where it's false, this section. And otherwise it's true. So like regarding the true value of implication in Venn diagrams, you just take one section, which is false, and mark everything else to be true. This is the same thing, essentially, just this is X-ray implies Yankee, this is X-ray is being implied by Yankee, or also Yankee implies X-ray, and so on. It doesn't matter, like, you just have to keep the order. somehow. So this is the same thing, just swapped, because now Yankee is the first one and X-ray is the second input. So you can see it's just symmetrical. And from the beginning we have NAND, NAND being the negation of AND. Visually on Venn diagrams it looks like we just swap the colors. The empty becomes colored and the colored becomes empty. That's the negation at the same time. So you can see the negation right here. So it is true if it is actually false if and only if both of them are true, and otherwise it's true. So you have to find the intersection, mark it false, and everything else is true. For no, again, negation of or, we work similar as AND, as we showed it before. We have to find the section where none of those are true. So where it's, here is X-ray, here's Yankee, here are both, and here's none. So here's nothing, and that's the only section that will be true. So nor is true if and only if none of the inputs are true, and otherwise it's false. For XNOR, we have to have exactly both of them or none of them. So like they have to be true at the same time. So here we have just X-ray, not Yankee, so no. Here's just Yankee, not X-ray, so no. Here are both, so yes. And here's none. None, yeah, they're true or false at the same time, so yeah. And the last one we already did. Okay, so that's all the 8 binary operations, and the negation is hidden, as I said, from 1 to the second in these 3 cases. Not the 4th one, because this is just like swap order of inputs, and this implication is not negation of the second implication. They're just kind of swapped. I would know the term in Czech. I don't know the term in English. However, if you want to like swap the implication, then this implication is the same. I'll use the equivalency or the biconditional sign. Is the same if you swap the inputs and mark them with negations. Then this would be the same. Or if I maintain the order of like the letters, then this would look like this. And this is actually equivalent, and they would have the same, like the same image. You can try to mark this down, and you'll see that it's actually this image. And the same with the second equivalency, just you know, swap the order of the arrows. So I think that's kind of totally it. I may overshot it a bit. However, if you have any questions, comments, or anything, just leave them down in the section below. And I hope you enjoyed. This was Tortoise, and see you. Bye bye.